Hello and welcome to this new video. In this video, I'm going to start chapter 2 about countable Markov chains. So I will cover the first two sections, definitions and examples, and I will talk about positive recurrence and limiting probabilities. Okay, so Markov chains on infinite sets have the same definition actually on finite sets. So all the definitions actually that we studied in chapter 1, communication classes, irreducible chains, recurrent states, transient states, period of a state, all these definitions are the same. And most of the results, actually all of the results except 3 that I will state now, actually still hold in the infinite countable set case. There are 3 results that remain partially true. There is corollary 1.4, theorem 1.1, and proposition 1.13. So I will just restate them and tell you what still is true. Okay, so corollary 1.4 is no longer true because and if we have a finite Markov chain or a Markov chain on a finite state with transition matrix P, if it's irreducible and aperiodic, then all the powers of P have, so Pn has positive entries for all n large enough. Okay, now in the case of an infinite, of a Markov chain on an infinite set, we have an infinite matrix P to the n. Okay, so this result is no longer true when the state is infinite because the matrix is infinite. Okay. This is, if you go back to the proof of this, you will see that we took at some point the maximum of a number in the set S. So, and this maximum, if the set is infinite, does not necessarily exist. Okay. Now, theorem 1.1 is not true, but the implications 3 implies 1 and 2 implies 1 are still true. If you look at their proof, you will see that they are still true. Okay. But 1 implies 2 is no longer true because 1 implies 2 is just corollary 1.4. Okay, so, and the third result is proposition 1.13 that we used many times. It tells us that if you have an irreducible Markov chain on a finite set, and if you denote by mu j the mean time of return to state j starting from state j, then actually the relation between the stationary distribution and mu j are given by this relation. They are inverse one of another. Okay, so use this result several times. But please don't confuse this mean time of first return with the mean time till the end of the game, because these two situations are completely different. Okay, we use the same notation, unfortunately, but it depends on the context. Okay, here we are in the context of a recurrent state usually. In the context of a game with an absorbing state, we use the same symbol, but to denote something different actually. Okay, so don't confuse them. And it will be clear from the context what do we mean by them. Okay, now let me give some important examples of Markov chains on infinite states, state spaces. The first example is the random walk on Z. So here we have, so the state space is at Z, and the system is jumping between the states, between the integers to the right with probability P and to the left with probability 1 minus P. Okay, so we just go one step at each time. So this is the random walk. Here the state space is infinite. Okay. And when P equal 1/2, we call this the symmetric random walk. Okay. Now, there is a formula for this random walk actually. Even if P is not 1/2, if Xn is this Markov chain and Yn is the sequence of independent random variable distributed according to this rule, so Yn takes the value 1 with probability P and the value -1 with probability 1 minus P, then I can write Xn plus 1 equal Xn plus Yn. So here we have the point of view of dynamical system. So xn plus 1 is really a function of xn and noise. Okay? But here we really need an infinite space. Okay, now we have also the symmetric random walk on Z square. So imagine an infinite grid of points where whose coordinates are integers, and a particle moves between the points of this grid. There are four. If you are in a state, if you are at a node ij, then we can move to either right or left or up and down. So there are four possibilities, each being equal. So this is the symmetric random walk on Z square. We can also generalize this by considering the symmetric random walk on Z to the D. Here we live in a D-dimensional space. So at each step, actually, we have, for example, when D equals 3, we have 8 possibilities now. Okay? And by symmetry, actually, Pij is 1 over 2D if I and j are neighbors. Okay? So these are the main examples of Markov chains on an infinite state space. Okay, now, so this concludes section 2.1. Now, section 2.2, we introduce a new kind of behavior. In the finite case state space, we had just two kinds of behaviors, recurrence and transience. And now in the infinite state space case, we have three behaviors: a transient, positive recurrent, and null recurrent. Okay, so there are two types of recurrence now, positive and null. What do we mean by that? By a recurrent state, actually mean that the probability, the conditional probability that Ti is finite starting from state I is equal to 1. But if the probability of this event is 1, it doesn't mean, usually if the state is infinite, it doesn't mean that the expectation is finite. Okay? So it's possible, this would be the case actually of the symmetric random walk on Z, which I'll see in a moment actually, that any state is recurrent, but the mean time of return, the expectation of the time of return, first return is infinite. So if in the case of a symmetric random walk on Z, all states actually are, if in the case of symmetric, so p equal 1/2, all states will be recurrent, but so if we start from a state, we are sure that we are going back, but the time of return may be very, very, very big, so that the mean time is infinite. Okay, this situation cannot happen in the finite state space. Okay, if you look at the proofs, for example, of proposition 1.13, we cannot have mu of I equal plus infinity if the state space S is finite. But this can happen when the state S is infinite. So this is one of the big differences. So if the mean time of first return, conditional mean time of first return is finite, we say that the state is positive recurrent. And otherwise, we say that I is null recurrent. So when you have an infinite mean time of return, first return, the state is null recurrent. Okay. Now, the first result about about Markov chains on infinite states is the following: there is an equivalence between the fact that state I is null recurrent, so mu I is plus infinity, and the fact that it is recurrent, which means that this series is divergent. We saw this in chapter 1. And however, the general term tends to 0. Now there's no contradiction, because so pay attention, if the series is convergent, then necessarily the general term tends to 0, but the converse is not true. So it's possible, and now we shall see some examples, that the general term of the series tends to 0, but the series is divergent, however. Okay? So saying there's an equivalence between saying that state I is null recurrent and saying that state I is recurrent, and the general term of the series goes to 0 as n tends to infinity. Okay, I will not prove this, You can see it in the references and the literature that I gave at the beginning of the lecture notes. But I will use this to prove something, to prove the fact that null recurrence and positive recurrence are class properties. Okay? So what does it mean? It means that if two states communicate, okay, according to our definition of communication that we gave in chapter 1, if one of them is null recurrent, the other is also null recurrent. So if I and j communicate, then we know that there is a path of length m going from I to j, and there is a path of length r going from j to I. Okay, and now, so recurrence is a class property, we know that. So I'm not going to prove that j is recurrent. Okay, I'm just going to prove that the general term of the series tends to 0. So, and for this, I use a corollary of the Kolmogorov-Chapman equation in this form. So PII to the m plus n plus r is bigger or equal than the product of these numbers. And therefore, in particular, when I divide by Pij to the m, Pjj to the n, I have this estimate of Pjj to the n. And now, since state I is null recurrent, this general term tends to 0 as n tends to infinity. So it follows that this also tends to 0 as n tends to infinity, and therefore state j is null recurrent. Okay, so now let us study the case of a random walk on Z. Now we have the tools to answer this question. So the bottom line is that the random walk on Z is transient if P is different from 1/2, and null recurrent if P equal 1/2. So it's recurrent in the symmetric case. Now, why is it transient in the non-symmetric case? Because there is a tendency, for example, if P is bigger than 1/2, then there is a tendency, there's a drift to the right. So there is a strong tendency of leaving, for example, state 0 and never going back. Okay, and if P is less than 1/2, there's a tendency to go to minus infinity. Okay, but in the symmetric case, we are sure that state 0, for example, or any other state, because they play the same role. So the random walk is irreducible, actually. But in the symmetric case, state 0 is recurrent, but it's null recurrent, not positively recurrent, because the chain can go to very far and then go back, but to go back needs a lot of time. So so times of first return can be arbitrarily large, and this is why their mean is infinite. This is the idea behind. Now, and how do you prove that? It's not difficult. We do some elementary combinatorics. So let us first prove that the random walk is transient if P is different from 1/2. Okay. Now, the first observation is that the period of 0 or any other state is 2, because to go from 0 to 0, we need a path or a loop of even length. Okay, you may draw a picture actually. If I want to go to 0, any loop of odd length will not go back to 0. Okay, so because I can just move to the right or left. So this means that the period of state 0 and therefore of any state is precisely 2. Okay, so if I want to go from 0 to 0, I can go from 0, 1 and from 1 to 0. This is, or 0 minus 1 minus 1, 0. This is length 2. It could be of length 4, for example, 0, 1, 2, 1, 0, or 0, 1, 0 minus 1, 0. So you see that the only loops or the only cycles from 0 to 0 have even length. Okay, so P00 to the 2n plus 1 is 0 necessarily. Now, if we want to start from 0 and return in 2n steps, which is the only possibility, what does it mean? It means that we have to go n step to the right and n steps to the left. This is the only possibility. Now, in how many ways can I go n steps to the right and n steps to the left? There are c to n ways to do that. And each way has probability p to the n times 1 minus p to the n, because by independence. Okay? So it's like a Bernoulli experiment. So therefore, the probability of starting from 0 and going back to 0 in 2n steps is given by c to n to the n times pn 1 minus p to the n. And so it's 2n factorial over n factorial p to the n 1 minus p to the n. Now, what happens when n is large? Because we are interested in the convergence and divergence of the series of this term. And for this, there is a simple formula due to Stirling that you probably know, is that asymptotically, n factorial divided by this quantity tends to 1 as n tends to infinity. So approximately n factorial is of the order of radical 2 pi n times n to the n times exponential to the power minus n. And therefore, I can find an equivalent of the general term of this series. If I apply Stirling formula, so I evaluate 2n factorial and n factorial squared, I get the simplification. I get 4 to the n times p to the n 1 minus p to the n over radical pi n. And this will solve the problem, actually. Because now, if p is different from 1/2, the numerator is strictly less than 1. So I have a geometric series here, and this series is convergent. So state 0 is transient. Okay, so the series of general term p0 to the n, which is the same as the series with even powers because the odd powers are 0. So this series is convergent, right? Because this is less than a geometric series of ratio less than 1. However, if p equal 1/2, this is precisely 1. The numerator will be just 1. So the general term, if it's not 0, will behave like 1 over radical pi n. And now the series whose general term is 1 over radical pi n is of course divergent. Therefore, the series p0 0 to the n is also divergent. Okay, and therefore, so this means that state 0 is recurrent actually. But how do you know that it's null recurrent and not positively recurrent? It's very easy because the general term tends to 0. So by the previous proposition, state 0 is null recurrent. It's recurrent, right? But it's null recurrent. Okay. So the symmetric random walk is null recurrent. So all states possess the same property because the chain is irreducible. Okay, so this concludes the first estimate. Next result, what about the general case, the symmetric random walk on z to the d? Okay, here we can do a similar reasoning, but the combinatorics are a little bit is more difficult. So I'll just give you the result. P00 to the 2n will be equivalent as n is big to a constant that depends on the dimension divided by n to the power d over 2. So remember that this is what we had in the case of d equal 1. When d equal 1, CD was just 1 over radical pi, right? Or so therefore, if n is so for d equal 1 or 2, this series is divergent. Okay, but for d is bigger or equal than 3, then d over 2 is bigger than 1. The series of general term 1 over n the d over 2 is convergent, and therefore we have transients in this case. Okay, so this is how we know that symmetric random walks on z to the d is only recurrent for the case in the case of a line and in the case of a plane. Okay, but for higher dimensional spaces, it's transient. So this result is very useful, actually. Okay, now I will end with 2 results without proof. This is just the kind of analog to the Ergodic theorem in the case of an infinite state space. So this is proposition 2.4. There is an equivalence between saying that the chain is positive recurrent and the fact that the chain has a stationary distribution. And in this case, the mean time of first return is given by the inverse of this limiting distribution. So same thing, actually. But note that the recurrence is not enough. We need positive recurrence. Okay. So in the case of finite state Markov chains, recurrence and positive recurrence are equivalent. Okay, this can be deduced from this proposition, but we knew that actually. Okay, we don't need to distinguish between null recurrent and positive recurrent in the case of a finite. They are just equivalent. Okay, but there is a difference in the infinite state space. Okay, so now let me give an example of a positive recurrent chain, because up to now the examples were just null recurrent. So I suggest that you draw a picture here. We have now a random walk on n, not on z, but with a kind of reflecting boundary at 0. Yeah, so we have a barrier. So we have 0, 1, 2, 3, etc. And there is a positive probability if we are at state 0, we can stay at state 0 with probability q. And otherwise, just a random walk with probability p to the right and q to the left, 1 minus p. So of course, you can check that all state communicate, so it's irreducible. And now, if we want to solve the system pi p equal pi, just can write the matrix actually. So you do it, you write the matrix, it's infinite in this case. And the linear system pi p equal pi is equivalent to saying that pi I is p over q to the I times p0. Okay, and since we want a probabilistic solution of the system, so the sum is 1, as you know. So this condition holds if and only if p is less than q. So p is less than 1/2. So we know that for p less than 1/2, so we have a tendency to go to 0 actually, the chain is positive recurrent. So this is an example of a positive recurrent Markov chain on an infinite state space. So, okay, so 0 here actually plays a special role. Okay. Okay. And so actually this result, proposition 2.4, was the equivalent of proposition 1.13. Okay. Now, the equivalence of the Ergodic theorem is this following theorem. So there's an equivalence between saying that the chain is irreducible, aperiodic, and positive recurrent, and the fact that Xn is ergodic. Okay, I will not prove this. You can see it in the literature because I don't have time anymore. So this is if you like, a general version of the ergodic theorem that we studied in chapter 1. So you note that recurrence is not enough. We need more. We need positive recurrence. And I will end with a result sometimes called the law of large numbers. So if you recall, what is the law of large number actually? It states that if we already encountered it in chapter 0, if you have a sequence of independent and identically distributed random variables with finite mean, then their sample average converges to their mathematical average. Okay, we know that. This is the strong law of large numbers. So this happens almost surely with probability 1. And it follows from this that if I have a bounded sequence, a bounded function f, if xn are IID, then f of xn is also IID, right, with finite mean. So the sample mean of f of xk also converges to the expectation of f of x0, one of them. So I can deduce this from this, right? Now, what is the interpretation here actually? The interpretation, So there is an analog of this for Markov chains, and so I don't need to assume the xn IID anymore. So there is a generalized version of this, and it's given by the following theorem. If I have an irreducible positively recurrent Markov chain, and pi denotes, we know that it has a stationary distribution, a limiting distribution pi. So if I have a bounded function f from the state space to R, then the time average of the xk, or the sample average, converges to this quantity, sum over all states of f of I times pi of I. Okay, now the strong law of large numbers is just a particular case of this. Okay, if you take the Markov chain to be just a sequence of IID. Okay, but let me give you an interpretation of this because it's important. What is the meaning of f in practice? So of this function f. It may represent, for example, the cost of visiting state I. Okay, so the average of all this f of xk is what represents the average cost of the chain up to time n. The quantity on the right is actually what is this space average. So what this theorem is saying is that a time average is converging to a space average. And in the theory of dynamical systems, this kind of theorems is called an ergodic theorem. So sometimes you will see this result stated as under the heading ergodic theorem. Okay, because there is a vast branch of mathematics called dynamical systems where topology mixes with probability, and we have such kind of things. Okay, ergodic theorems. So this is you may see this powerful theorem sometimes. Okay, and I will ask you, if you are interested, to find some actuarial applications of this theorem. Okay, how can this theorem be applied? Okay, to estimate the time average. So instead of computing this, sometimes it's easier to compute this, or vice versa. So when n is large, these two quantities, time average and space average, are very close together to themselves. So we can use one of them to compute the other, which one, whenever one is easier to. So I want you to do a small research about the possible applications of the ergodic theorem in actuarial sciences. Okay, so this concludes this video. Next time I will explain Galton-Watson processes, which also are very important. So thank you for your attention, and see you soon.